In the depths of the universe, beyond the realm of atoms, there exists a world where the unseen reigns, a world that challenges our intuition. But how did an ordinary light bulb illuminate the mysteries of this unknown universe? How did scientists confront the mysterious issue known as the ultraviolet catastrophe? And how did the photoelectric effect push the boundaries of classical physics and defy scientific expectations? A century ago, Einstein's groundbreaking theory revealed that light is indeed composed of particles. Yet, how did Rutherford uncover the secret at the heart of the atom? How do electrons remain in orbit without collapsing into the nucleus? And how did Bohr resolve this paradox? By discovering the wave nature of matter, how did Louis de Broglie expand the boundaries of the universe? And how did the Davison-Germer experiment prove that electrons behave not only as particles, but also as waves? As Heisenberg's matrix mechanics gave a structured form to the mysteries of the quantum world, why did Schrödinger argue that quantum mechanics should be deterministic? And how did the Copenhagen interpretation bring forth the idea of an observer-defined reality? What is quantum entanglement, that spooky action Einstein opposed? How did Dirac's equation reveal the existence of antimatter? And how did Pauli's exclusion principle redefine the entire field of chemistry? How did the mystery of fundamental forces in the universe unfold with quantum field theory? And how did electrons and light come together through quantum electrodynamics? Finally, how did John Bell propose a new approach to settle the debate on quantum reality? Does quantum mechanics reveal the ultimate structure of the universe, or does it open a door to far deeper secrets yet to be unraveled? Let's explore the answers to these questions in depth. How did the light bulb play a key role in the birth of quantum mechanics? When we peer into the depths of the universe, beyond the smallest building blocks of matter, we begin to notice certainty and familiarity gradually fading away. We encounter the strange and mesmerizing world of quantum mechanics. At the heart of everything we see lies a universe unlike our own. One of the pioneers of quantum mechanics once said, "Everything we call real is made of things that cannot be regarded as real." About a century ago, humanity's brightest minds embarked on a brave journey into the unknown, down the rabbit hole, into the strange and mysterious. In this enigmatic microcosm, they discovered that objects could exist in two places at once. They witnessed fate, shaped by the hands of chance. Reality itself defied common sense, forcing us to confront the idea that everything we thought we knew might be entirely different. This captivating journey began unexpectedly with a humble object, the light bulb. In the 1890s, Berlin, in the newly unified and industrial-hungry Germany, Edison's new invention, the light bulb, garnered significant interest. Several engineering firms spent millions to acquire the European patent for the light bulb. It was the essence of modern technology, a bright symbol of progress. Engineers realized they could make fortunes by illuminating the streets of the German Empire. However, what they didn't realize was that this seemingly simple invention would soon pull scientists into a profound mystery and ignite the spark of a scientific revolution. It was known that the filament emitted light when heated by electricity, but the exact way the filament produced light and the physical principles underlying this process remained a mystery. This marked the beginning of the question that laid the foundation for the birth of quantum mechanics. How did the ultraviolet catastrophe arise? The relationship between the temperature of a filament and the color of the light it emits held crucial clues about the fundamental nature of the universe. Solving this mystery was not just a step forward in technology. It was a quest to unlock the deepest secrets of nature. Driven by this goal, the German government established a research center in Berlin named the Imperial Physical and Technical Institute. In 1900, a brilliant mind, Max Planck, was appointed to lead the institute's work. When Planck pursued what seemed like a simple question, he found that the laws of classical physics were inadequate to explain this phenomenon. A new paradigm was needed to understand the nature of light and energy. This quest led to the revolutionary idea that energy is emitted in discrete packets, quanta. Planck's groundbreaking concept laid the foundation for quantum mechanics, radically transforming our understanding of the universe. The light bulb was no longer just a device that illuminated darkness. It became a gateway to the mysterious world of atoms and particles. So why does the color of light change as the filament heats up? To understand the puzzle Planck faced, let's consider a simple experiment, heating a metal rod gradually. At first, the rod emits no light. As it heats up, it begins to glow with a deep red hue. With increasing temperature, the color shifts to orange and then to yellow. But no matter how much we heat it, the rod does not emit blue light. Why doesn't the color of light continually progress toward blue? To solve this mystery, Planck and his colleagues designed a device they called a blackbody radiator. This consisted of a specialized furnace with precisely controlled temperatures and an apparatus to measure the frequency of emitted light. Over a century later, scientists are still working to refine such measurements. For example, in a laboratory setting, when the internal temperature of the furnace reaches 841 degrees Celsius, the furnace glows with an orange-red hue. This is the color of light observed at lower temperatures. When the temperature is raised further to around 2000 degrees Celsius, the furnace emits a much brighter, whitish light. Producing light of this intensity and color requires approximately 40 kilowatts of power, an enormous amount of energy. Even though the light appears whiter, it still has a reddish-white tint and contains very little blue light. Why is it so much harder to produce blue than red? At higher regions of the spectrum, beyond blue, in the area we call ultraviolet, even objects as hot as the sun emit very little light. Despite the sun's surface temperature of 5,500 degrees Celsius, it mostly emits white, visible light, producing surprisingly little ultraviolet light. Why do even the hottest objects in the universe fail to emit more ultraviolet light? Why is it so challenging to produce ultraviolet light? This extraordinary issue left scientists deeply puzzled in the late 19th century. Classical physics theories predicted that objects at high temperatures would emit an infinite amount of high-energy light. However, experimental data contradicted these predictions. This contradiction became known as the ultraviolet catastrophe. How did the photoelectric effect challenge existing science? To solve the ultraviolet catastrophe, Max Planck took the first steps toward one of the deepest revolutions in 20th century physics. He discovered a definitive relationship between the frequency of light and its energy, a strange mathematical connection that shaped the world of particles and waves. However, Planck did not fully grasp the profound meaning of this relationship. But things were about to get even stranger. Toward the end of the 19th century, scientists were studying newly discovered radio waves. To understand how these mysterious waves were transmitted, they set up various experimental devices. Most involved producing a spark by causing an electric discharge in the gap between two metal spheres. However, while conducting these experiments, they encountered something unexpected. When strong light was shone on the spheres, the sparks occurred more easily. This indicated a mysterious connection between light and electricity. To study this connection more closely, scientists developed a gold leaf electroscope, a more sensitive version of the spark gap apparatus. This device worked by electrically charging two thin gold leaves attached to a metal rod. When electrons were added and the device was negatively charged, the gold leaves, bearing the same electric charge, would repel each other and stay separated. When used to investigate the effects of light on electrical charge, the electroscope opened the door to a remarkable discovery. First, when red light was directed at the metal, the gold leaves remained separated. No matter how bright the red light was, it did not affect the static charge keeping the leaves apart. This suggested that red light lacked the energy needed to interact with the metal. However, when blue light, especially ultraviolet light, was directed at the same surface, the situation completely changed. The gold leaves immediately closed, as the blue light possessed the power to release electrons from the metal surface. In this case, ultraviolet light had enough energy to mobilize the electrons, thus affecting the charge on the leaves. This phenomenon was termed the photoelectric effect. It demonstrated that the energy of light was linked to its frequency, and thus its color. In other words, the energy of light was directly related not just to its intensity, but also to its frequency. Since red light had a low frequency, it lacked the necessary energy, whereas blue or ultraviolet light, with a high frequency, could move electrons thanks to its sufficient energy. The photoelectric effect laid the groundwork for quantum mechanics by showing that light behaved not only as a wave, but also as a particle carrying specific amounts of energy. For physicists, the ultraviolet catastrophe and the photoelectric effect were pieces of a grand puzzle. Even with the best scientific knowledge available at the time, these phenomena could not be explained. Science had definitively asserted that light was a wave. When we observe the world around us, we can see light behaving in a logical, wave-like manner. The blur at the edges of shadows, for instance, can be explained by the diffraction of light bending around obstacles, a characteristic behavior of waves. What about clouds in the sky? When sunlight passes through the water droplets within clouds, stunning patterns of rainbow colors are formed. Light reflects and refracts off these droplets, separating into colors, much like the interactions between waves on a water surface. This provides a vivid demonstration of light's wave nature. These observations led us to accept as fact that light was a wave. But while the wave theory could beautifully explain such phenomena, it was insufficient to understand the ultraviolet catastrophe and the photoelectric effect. When dealing with these mysterious phenomena, it was as if the wheels had come off. The problem was, how could light behave in such a way? To grasp this puzzling phenomenon, a different perspective could be useful. Consider, for example, the impact of large ocean waves crashing against rocks on the shore. Small waves do not affect the rocks, but large waves exert tremendous pressure and can wear down the rocks. More intense waves carry more energy and can influence the objects around them. The implication is clear. Larger, more intense waves bring more power. If light truly behaved like a wave, greater intensity should cause more electrons to dislodge. But in reality, this was not the case. No matter how intense red light was, it would not budge the electrons in the metal, while a faint ultraviolet light had a significant effect, dislodging electrons within seconds. Thus, thinking of light solely as a wave did not align with these observations. Solving this puzzle required someone to think beyond the ordinary. How did Einstein explain the photoelectric effect? In 1905, Albert Einstein proposed a revolutionary theory to explain the photoelectric effect, challenging traditional views about light. At the time, light was widely accepted to be a wave. However, Einstein presented a radical perspective that required us to imagine light as a stream of small, energy-loaded particles. Einstein called these light particles quanta. A quantum was a specific packet of energy. While the term itself was not new, the idea that light consisted of such quanta seemed almost unbelievable to many at the time. Following this radical idea to its logical conclusion offered a simple and elegant solution to the mysteries of light. To make it clearer, let's use an analogy to understand how Einstein explained the photoelectric effect with his particle model of light. Imagine light quanta as marbles being thrown at a target. In this analogy, the targets the marbles hit represent the electrons within the metal. In the original experiment, when light was shone on the metal, electrons were ejected from the surface, generating an electric current. Low-energy red light is like gently thrown, lightweight marbles. No matter how many marbles are thrown, they don't have enough energy to knock the electrons out of place when they hit the target. Now let's imagine throwing fast, energetic marbles, similar to high-frequency ultraviolet light. Even if fewer marbles are thrown, these energetic marbles hit the target with enough energy to dislodge the electrons. Einstein's claim was this: each quantum of light is a particle with energy determined by its frequency. Because red light has a low frequency, its quanta carry little energy, while ultraviolet light has a high frequency, meaning its quanta carry much more energy. This simple but profound idea perfectly explained the photoelectric effect. Moreover, Einstein's elegant approach also helped resolve Planck's dilemma regarding the puzzle of radiant bodies. The reason ultraviolet light is less abundant than red light is that it requires significantly more energy, about 100 times more, to produce ultraviolet quanta. Thus, high-frequency light consists of rarer but more energetic quanta. This moment at the dawn of the 20th century marked the beginning of a true revolution. Physics, as applied since Newton, Laplace, and others, was shown to require a completely new approach. From that point forward, physics changed irreversibly, and modern physics truly began here. However, Einstein's theory left physicists with a dizzying paradox that defied all intuition. Could light be both a wave and a particle? This duality opened the doors to the mysterious and mesmerizing world of quantum mechanics. How did Rutherford uncover the secret at the heart of the atom? Einstein's theory of light revealed a relationship between matter and energy in a way never before considered, sparking a revolution in the world of physics. However, in light of these new discoveries, the internal structure of the atom itself also became a central topic of discussion. How are the fundamental particles that make up matter actually arranged? This question had become one of the most intriguing questions of the era. By 1911, a scientist named Ernest Rutherford was preparing an experiment that would unveil the mysteries of the atom's internal structure. Rutherford realized that the atom was far more complex than previously thought. To make this discovery, he directed positively charged alpha particles at a thin sheet of gold foil. According to the prevailing view, these particles should have passed almost straight through the foil, as it was believed that the atom had a homogeneous structure. However, something unexpected happened in Rutherford's experiment. While most of the alpha particles did indeed pass through the foil, some of them bounced back as if they had struck an invisible wall. This observation left Rutherford deeply astonished. Could an atom have a core powerful enough to deflect the alpha particles passing through it? Yes, at the center of the atom, there existed a tiny but immensely dense concentration of positive charge. This discovery led to the idea that at the heart of the atom lies a very dense and small structure known as the nucleus. Rutherford's model depicted the atom as having electrons orbiting this nucleus, like planets revolving around a small star in the vast emptiness of space. These electrons moved in specific orbits around the nucleus, much like planets orbiting the sun. This new model of the atom was revolutionary for science's understanding of the material world. Matter was no longer perceived as a homogeneous structure, but rather as a miniature universe containing a remarkable order within it. Why didn't electrons fall into the nucleus? What was Bohr's solution? The emergence of Rutherford's atomic model opened a new door to scientific knowledge about matter. It became understood that the atom was largely composed of empty space, with a dense nucleus at its center and electrons orbiting around it. However, this model presented a challenging paradox within the limits of classical physics. As electrons orbit around the nucleus, they are constantly accelerating, meaning they should lose energy. This loss of energy would inevitably lead to them slowing down and eventually spiraling into the nucleus. Yet, this wasn't happening. How was the atom able to maintain its stable structure without falling apart? This question led Danish physicist Niels Bohr on a deep quest for a solution. In 1913, Bohr began developing a new atomic model, inspired by the quantum theories of Einstein and Planck. Max Planck had proposed that energy was emitted in discrete packets, quanta. Einstein had then used this idea to explain the photoelectric effect, suggesting that light carried energy in such packets. Bohr applied these groundbreaking ideas to the inner workings of the atom and introduced a revolutionary approach to the behavior of electrons. Bohr's model predicted that electrons were not located in arbitrary orbits, but could only exist in specific quantized orbits corresponding to certain energy levels. Electrons would not lose energy while moving in these special orbits. However, when they transitioned from one energy level to another, they would emit or absorb a specific amount of energy. This was the critical innovation of Bohr's atomic model. Electrons within the atom could only move in certain orbits, with each orbit serving as a keystone for the atom's stability. The jumps of electrons between these energy levels also explained the distinct lines in an atom's light spectrum. Each energy level corresponded to a unique spectral line. For instance, the hydrogen atom emitted characteristic lines due to electrons occupying specific energy levels. When Bohr compared this theory to existing experimental data, especially the Rydberg formula that explained the spectral lines of hydrogen, he found that his model worked with remarkable accuracy. Bohr's atomic model demonstrated that there was a profound order and harmony within the atom. The atom was no longer seen as containing freely moving particles, but as a system operating with a complex arrangement and rhythmic jumps. This model revealed the stability of the atom and the discrete nature of energy levels, showing how quantum rules shaped matter. How did de Broglie uncover the wave nature of matter? Bohr had explained the stable structure of the atom by proposing that electrons only moved in certain orbits with specific energy levels. However, these explanations didn't entirely unravel the mystery behind the fundamental nature of matter's smallest building blocks. Were electrons simply tiny particles, or did they have a much deeper nature? In 1924, a young French physicist named Louis de Broglie proposed a hypothesis that would challenge this question. At the time, there was a focus on the fact that light could behave either as a particle or as a wave, depending on the experiment. But Louis de Broglie asked a different question. What about electrons? If light sometimes behaved like a wave and sometimes like a particle, perhaps electrons, thought to be particles, could also behave like waves. In other words, maybe electrons had a wavelength associated with them. With these thoughts, de Broglie aimed to create a broader framework that encompassed both light quanta, photons, and particles that could behave as waves. De Broglie proposed that everything in the universe could act either as a particle or as a wave, depending on the experiment, and he sought a way to determine the wavelength of these entities. This wavelength is now known as the de Broglie wavelength. However, this was only a hypothesis. De Broglie didn't prove this claim. He merely introduced the idea, leaving experimentalists to test it. De Broglie suggested that the wavelength associated with matter could be calculated by dividing Planck's constant by the momentum of that matter. For example, the wavelength of an electron could be calculated in this way. But why Planck's constant? Planck's constant is a fixed value that appears in various experiments, such as the photoelectric effect and blackbody radiation. 6.626 x 10 circumflex, minus 34 joule seconds. It's an extremely small number and a fundamental constant in modern physics. An earlier equation related to the wavelength of light also influenced de Broglie's proposal. The wavelength of light could be calculated by dividing Planck's constant by the momentum of photons. Although photons have no mass, Einstein's theory of relativity showed that light could still have momentum. This can be explained by an equation expressing the relationship between energy, rest mass energy, and momentum. Since light has zero rest mass, the equation simplifies, allowing us to find the wavelength of light in this way. De Broglie hypothesized that this equation could also apply to particles other than light, such as electrons, protons, and neutrons. According to him, these particles could also have a wavelength. Some critics suggested that de Broglie was merely applying known equations to material particles, but in reality, his contribution went far beyond that. His hypothesis was far-reaching and made numerous contributions to modern physics. De Broglie's work helped explain many previously incomprehensible formulas in quantum mechanics and provided a framework to justify why the Bohr model of the atom worked. How did the Davison-Germer experiment prove the wave-particle nature of electrons? To test the wild idea proposed by Louis de Broglie, Clinton Davison and Lester Germer conducted a groundbreaking experiment in the mid-1920s, investigating the wave properties of electrons. The primary goal of their experiment was to observe how electrons behaved when interacting with a crystal surface. If electrons truly possessed wave characteristics, they would create diffraction and interference patterns upon interacting with a crystal lattice, similar to how light behaves when it passes through a grating. In the Davison-Germer experimental setup, electrons were accelerated from an electron gun with a specific energy and directed at a well-ordered nickel crystal. The regular arrangement of atoms in the nickel crystal acted as a diffraction grating that could reveal the wave properties of electrons. When electrons hit the crystal, some reflected off the surface, while others penetrated the crystal. Initially, the researchers aimed to study how electrons reflected off the nickel surface. However, due to an unexpected malfunction, the nickel crystal was exposed to high temperatures, which altered its structure and allowed for more distinct diffraction patterns to be observed. If electrons acted solely as particles, there would be no reason to expect concentrations of reflections at specific angles. However, the experimental results showed that electrons reflected at certain angles intensified, proving the wave-like nature of electrons. Davison and Germer then observed how changing the energy of the electrons affected the diffraction patterns. As the energy increased, the wavelength of the electrons shortened, shifting the positions of the diffraction patterns. In another phase of the experiment, even when electrons were sent one at a time, an interference pattern gradually appeared on the screen over time. This finding demonstrated that each electron could interfere with itself through its wave function, suggesting that electrons have a probabilistic nature. The work of Davison and Germer provided striking confirmation that electrons could exhibit both particle and wave properties. These findings supported the principle of superposition in quantum mechanics. Instead of traveling in a single path or a defined point, electrons tended to travel through all possible paths. This meant that the exact position of electrons could not be determined and could only be described in terms of probability distributions. The results of the Davison-Germer experiment generated great excitement in the physics community and validated de Broglie's hypothesis. It was experimentally shown that electrons displayed wave properties, giving a significant boost to the development of quantum mechanics. Around the same period, the The double-slit experiment also played an important role in demonstrating the wave-particle duality of electrons. When light passed through a double slit, it created interference patterns, revealing its wave nature. A similar experiment with electrons produced the same results. When electrons passed through a double slit, interference patterns appeared on the screen. Remarkably, even when electrons were sent one at a time, the accumulated data over time still formed interference patterns. This showed that the wave functions of electrons passed through both slits and interfered with themselves. How did Heisenberg's matrix mechanics provide a concrete mathematical structure for the quantum world? Following Davison and Germer's experiment, which revealed the wave-like behavior of electrons, it became increasingly clear that classical physics was insufficient to explain the subatomic world. In 1925, recognizing this limitation, Werner Heisenberg adopted a radical approach by focusing only on directly observable quantities, rather than unobservable orbits and exact positions. This new perspective led to the birth of matrix mechanics, the first consistent mathematical formulation of quantum mechanics. Traditional physics described nature using differential equations and continuous functions, but Heisenberg showed that these concepts did not apply at the subatomic level. Instead, he used matrices to represent physical quantities and their interactions. These matrices contained information on transitions between energy levels and probability amplitudes, allowing him to develop a theory based solely on observable phenomena. This approach abandoned the deterministic nature of classical physics, replacing it with a probabilistic and statistical understanding. Instead of precise positions or velocities, probability distributions and energy transitions became central to describing subatomic particles. Heisenberg's model described an electron's behavior not by a fixed orbit, but through probabilities. Heisenberg's work was further developed with the contributions of other pioneering scientists, such as Max Born and Pascual Jordan. Together, they established a solid mathematical foundation for matrix mechanics and formulated the laws of quantum mechanics. This theory achieved great success in calculating atomic spectra and matched well with experimental data. One of the most striking aspects of matrix mechanics was that the product of physical quantities was generally non-commutative, meaning for quantities A and B, AB was not equal to BA. This challenged fundamental principles of classical physics and offered deep insight into the nature of measurements in the subatomic world, showing how profoundly different it was from our everyday experiences. Heisenberg's matrix mechanics opened the door to a new understanding of reality's nature. The mysterious and uncertain nature of the subatomic world became comprehensible within this new mathematical framework. The physical world was no longer functioning as a deterministic machine, but as a domain governed by probabilities and uncertainties. Why did Schrödinger argue for a deterministic quantum mechanics? Heisenberg's matrix mechanics was a major step in understanding the complex and mysterious nature of the quantum world. However, this abstract and mathematically intense approach was not intuitive for many. Austrian physicist Erwin Schrödinger, who wanted a more visual, wave-based perspective on the depths of the universe, decided to take a different approach. In 1926, Schrödinger developed a theory that would radically alter our view of quantum mechanics: wave mechanics. Schrödinger argued that particles did not merely exist at a single point, but also spread across space like actual physical waves. According to him, electrons and other subatomic particles were not located at a single position, but existed as real waves spread out in space. This meant that the behavior of particles could be described by a mathematical construct called a wave function. The wave function represents the spatial distribution and time evolution of a particle. In Schrödinger's approach, this wave function had physical reality. It demonstrated that particles existed as waves in space. However, in the same year, Max Born suggested that the wave function should be interpreted not as a physical wave, but as a probability amplitude that gives the likelihood of finding a particle at a particular location. This interpretation laid the foundation for the Copenhagen interpretation, which embraces the probabilistic nature of quantum mechanics and asserts that the absolute square of the wave function gives the probability density. Schrödinger strongly opposed this probabilistic interpretation and the notion that the wave function was merely a probability wave. In his view, quantum mechanics should be deterministic, and the wave function should represent real physical waves. Particles existed in space as waves with a definite energy and momentum, and their behavior could be governed by precise physical laws. Schrödinger's deterministic approach offered an understanding of reality closer to our everyday experiences and intuition. However, proponents of the Copenhagen interpretation argued that the quantum world was fundamentally probabilistic and dependent on the observer. Schrödinger disagreed with this indeterministic, observer-dependent view of reality. To illustrate the inconsistencies of the Copenhagen interpretation, Schrödinger devised his famous Schrödinger's cat thought experiment. In this scenario, a cat is placed in a superposition of being both alive and dead, contingent upon the decay of a radioactive atom that triggers a mechanism. Schrödinger used this paradox to emphasize that the probabilistic interpretation of quantum mechanics could lead to absurd conclusions for macroscopic objects. How did the Copenhagen interpretation place the observer at the center of reality? In 1927, one of the most intense debates in intellectual history took place in Copenhagen. Danish physicist Niels Bohr and his young colleague Werner Heisenberg came together to understand the mysterious nature of the quantum universe. This profound exchange of ideas at Bohr's Institute resulted in a revolutionary approach to quantum reality, the Copenhagen interpretation. The Copenhagen interpretation challenged the classical concept of definite reality by introducing a new understanding in which certainties were replaced by probabilities in the quantum realm. According to this interpretation, a particle's wave function represents the probability of it being in a particular location or energy level. Rather than a single absolute reality, it points to potential states shaped by probabilities. Particles do not possess definite properties until they are observed. Instead, they exist in a superposition of different probabilities. The act of observation plays a crucial role in this context. According to the Copenhagen interpretation, a particle only transitions to a definite state through observation. When observed, the wave function collapses, and the particle shifts from a sea of possibilities to a single, specific state. This process demonstrates how observation shapes reality in the quantum world. In the absence of observation, the universe exists as a sea of possibilities and potential states. One of the key pillars of this quantum understanding is Heisenberg's uncertainty principle. This principle states that it is impossible to simultaneously know a particle's exact position and momentum, the product of mass and velocity, with perfect accuracy. At the quantum level, the more precisely one property of a particle is measured, the more uncertain the other becomes. This arises not from the limitations of measurement tools, but from the fundamental nature of reality. The uncertainty principle reveals the inherent indeterminism and probabilistic nature of the quantum world. In this light, the concept of measurement became crucial in the quantum realm. Niels Bohr introduced the principle of complementarity to explain this dual nature of the quantum world. According to this principle, particles can exhibit both wave and particle characteristics, but it is impossible to observe both simultaneously. When we measure one property, information about the other is lost. For example, when we observe electrons creating interference patterns as waves, we cannot determine their exact position. Conversely, when we measure electrons' specific position, we lose insight into their wave behavior. According to Bohr, these two properties complement each other, and both are necessary to fully understand quantum phenomena. This demonstrates that nature is not defined by a single certainty, but by a whole that emerges from different observations. The Copenhagen interpretation highlights the complex and nuanced reality of the quantum world, representing a significant departure from the deterministic universe envisioned by classical physics. This new approach embraces a universe that is fundamentally probabilistic and interactive with the observer. Reality is shaped by the interaction between the observer and the system, meaning that measurement and the observer play a central role in physical processes. What is quantum entanglement, and why did Einstein oppose it? Einstein never accepted the probabilistic approach proposed by the Copenhagen interpretation. By asking, "Does the moon cease to exist when I'm not looking at it?" he argued that reality must exist independently of observation. In his view, our understanding of how the universe operates should be fully precise. There must be an underlying order and certainty in nature. He saw the probabilistic and uncertain structure introduced by quantum theory as a flaw in the theory itself. For this reason, Einstein engaged in a passionate debate with Niels Bohr about whether quantum mechanics truly represented reality. In 1935, along with Nathan Rosen and Boris Podolsky, Einstein developed the Einstein-Podolsky-Rosen (EPR) paradox to demonstrate what he saw as the incompleteness of quantum mechanics. The EPR paradox embodied Einstein's belief that there must be something deeper in the workings of nature. At the heart of this debate was a fascinating phenomenon known as quantum entanglement. Entanglement describes the unique and mysterious bond between two particles created simultaneously and identically. Regardless of the distance between them, measuring the state of one particle instantly influences the state of the other. Imagine two particles at opposite ends of the universe that suddenly align with each other the moment we observe them. Einstein called this spooky action at a distance, and argued that the nature of this interaction contradicted the theory of relativity. In a universe where nothing could travel faster than light, two particles influencing each other instantaneously was, for Einstein, an unacceptable flaw of the Copenhagen interpretation. Such spooky behavior could not exist in the fundamental structure of the universe. According to Einstein, the properties of entangled particles must be definite before observation. This idea can be illustrated with the example of a pair of gloves. If a left and right glove are placed in separate boxes, upon opening one box and finding the right glove, you would know the other box contains the left glove. The properties of the gloves were determined from the beginning. Opening the boxes did not change them. Therefore, Einstein argued that quantum particles must also have definite states before any measurement is made. In his view, the universe should not transform based on our observations. Reality should exist independently of observation. Bohr, however, had a different perspective. Relying on the experimental results of quantum mechanics, he argued that the states of particles are only determined at the moment of measurement, and that without an observer, these states exist only as probabilities. To Bohr, entanglement was a fundamental aspect of the universe that defied classical logic. It required a new way of thinking about nature, a different perspective on reality. By the late 1930s, as the world stood on the brink of war, this debate reached a temporary impasse. Physicists, engaged in their struggle to uncover the deepest mysteries of nature, were compelled to focus on the more immediate needs of humanity and the war effort. Many scientists emigrated to the United States, and in the post-war period, quantum theory made rapid advancements in technological applications. The philosophical debates surrounding the theory's foundations were temporarily set aside. How did Dirac's equation reveal the existence of antimatter? In 1928, English physicist Paul Dirac set out to develop an equation that would unify quantum mechanics with Einstein's theory of special relativity. At that time, the Schrödinger equation formed the foundation of quantum mechanics, but it did not fully explain the behavior of particles moving at relativistic speeds. Dirac aimed to describe the motion of electrons within a relativistic framework, striving for a deeper understanding of the subatomic world. The result of Dirac's intense efforts, the Dirac equation, naturally explained quantum properties such as electron spin and magnetic moment. This equation expressed the electron's wave function as a four-component spinor, thus solidifying the mathematical basis of the spin concept. However, the equation also produced an unexpected result: solutions for both positive and negative energy. The negative energy solutions sparked significant debate among physicists. Initially, these solutions were seen as non-physical mathematical anomalies and were dismissed. However, Dirac proposed that these negative energy states might represent a physical reality. According to him, these states hinted at the existence of a type of particle not yet discovered in nature. Taking a bold step, Dirac proposed that every particle must have an antiparticle. That is, there must be a particle with the same mass as an electron, but with an opposite electric charge. This was the theoretical prediction of antimatter, a form of matter not yet observed in nature. Dirac named this new particle the positron, and believing in the power of mathematics to describe nature, he predicted that this finding would eventually be experimentally confirmed. This prediction was met with both excitement and skepticism in the scientific world. The concept of antimatter was considered purely theoretical, or something found only in science fiction. Dirac's claim that such an entity truly existed, based on mathematical derivations, led physicists to question fundamental assumptions. Yet Dirac continued his work, convinced that mathematics spoke the language of nature. Only 4 years after Dirac's prediction, in 1932, American physicist Carl Anderson observed traces of a particle similar to the electron, but with a positive charge during experiments on cosmic rays. Anderson named this newly discovered particle the positron, thus providing experimental confirmation of Dirac's prediction of antimatter. This discovery sparked a scientific revolution, profoundly impacting our understanding of the structure of matter and energy in the universe. The discovery of antimatter raised new questions in the fields of physics and cosmology. This symmetry between matter and antimatter led to questions about why, following the Big Bang, the universe is dominated by matter. Where did the antimatter go? Why is the universe primarily composed of matter? These fundamental questions have engaged physicists and philosophers alike, leading to new theories about the origin of the universe. The innovations brought about by Dirac's equation extended beyond this. By providing a more comprehensive explanation of electron behavior, the equation played a crucial role in our understanding of atomic and subatomic processes. The spin properties and magnetic moments of electrons emerged as natural consequences of this equation, offering a deeper understanding of atomic structure and the nature of chemical bonds. The concept of antimatter has also found significant applications in technology. Today, antimatter is used in medical imaging techniques such as positron emission tomography. This technique uses gamma rays produced by the interaction between positrons and electrons to obtain detailed images of the internal structure of the human body. In addition, antimatter particles are produced in particle accelerator experiments, pushing the boundaries of fundamental particle physics research. How did Pauli's exclusion principle reshape chemistry? In 1925, Austrian physicist Wolfgang Pauli introduced a groundbreaking principle to explain the complex structure of atoms and the energy levels of electrons within them. At that time, the internal structure of atoms and the arrangement of elements in the periodic table were not fully understood. Quantum mechanics fell short in explaining the behavior of electrons within atoms, and a deeper understanding was needed. Pauli, by examining the energy levels of electrons in atoms and why these levels filled in a specific way, formulated the Pauli exclusion principle. According to this principle, no two electrons within an atom can occupy the same quantum state, meaning they cannot have the same set of quantum numbers. In other words, each energy level can only accommodate a certain number of electrons, determining the structure and chemical properties of atoms. This principle was critical for explaining why electrons fill specific energy levels and why the periodic table has its current structure. Pauli's exclusion principle showed that electrons have a property called spin, which can only take two possible values. This meant that each energy level could hold a maximum of 2 electrons, and these electrons must have opposite spins. Interestingly, the concept of spin is directly related to Dirac's equation. While Dirac explained the relativistic behavior of electrons, he naturally derived the concept of spin. Pauli's exclusion principle, which determines the statistical behavior of particles with spin, fermions, in quantum mechanics, complemented Dirac's work by helping us understand the relativistic properties of these particles. Together, the contributions of both scientists provided a deeper understanding of the fundamental nature of matter and antimatter. The Pauli exclusion principle helped us understand the shell structure of atoms and how these shells fill. This became a fundamental factor in determining the chemical properties and reactivity of elements. The periodic table was now arranged logically according to atomic numbers and electron configurations, making it possible to predict the chemical behaviors and bonding tendencies of atoms. This discovery sparked a major revolution in both chemistry and physics. Understanding the internal structure of atoms allowed for a deeper exploration of chemical reactions and the properties of matter. Pauli's work showed that electrons are defined not only by energy levels, but also by quantum states. This was a significant step in the development of quantum mechanics and particle physics. The Pauli exclusion principle became a general rule for a class of particles known as fermions. Particles like electrons, protons, and neutrons cannot share the same quantum state. This principle plays a crucial role in understanding the behavior of matter in solid, liquid, and gas phases, as well as the properties of cosmic structures like white dwarf stars and neutron stars. For example, one of the forces preventing white dwarf stars from collapsing is the inability of electrons to share the same energy level due to the Pauli exclusion principle. By explaining the arrangement of fundamental particles that make up matter, Pauli's principle strengthened the bridge between physics and chemistry. The stability of atoms and molecules as well as properties like density and hardness, are direct consequences of this principle. It also provides a foundation for advanced topics in physics, such as superconductivity and quantum states. This principle gave scientists a clearer perspective on the microscopic world of matter. The complex behaviors of atoms and molecules could now be explained with quantum mechanical principles and the Pauli exclusion principle. This has also been instrumental in technological advancements and the development of new materials. How did quantum field theory reveal the fundamental forces of the universe? In the 1930s, the world of physics was on the verge of taking a step closer to understanding the mysterious fabric of the universe. Quantum mechanics explained the behavior of subatomic particles successfully, while the theory of special relativity described the behavior of objects moving at high speeds. However, there was an inconsistency between these two theories. There was no consistent framework that could combine quantum mechanics with special relativity. To fill this gap, physicists developed a new approach known as quantum field theory. Quantum field theory showed that particles and fields are actually inseparable from one another. Particles were defined not only as solid entities, but also as excitations of fields. Quantum fields provided a deep insight into the microscopic workings of the universe, encompassing processes such as the creation and annihilation of a particle. This new understanding revealed that energy and matter were in a continuous interaction at the subatomic level. In the fabric of the universe, a field had to exist before a particle could emerge, and the quantum nature of these fields created and annihilated particles. Through the quantization of these fields, it became possible to understand the nature of the electromagnetic force. We now knew that the electromagnetic force interacted through quantized excitations of fields known as photons. This idea served as a key to explain the other fundamental forces in the universe as well. This revolutionary framework laid the foundations for the Standard Model, showing how protons, neutrons, electrons, and many other particles came together and interacted. Quantum field theory provided another insight by allowing us to understand the cycle of particle birth and death. These field excitations involved not only the creation and annihilation of particles, but also the existence of antiparticles. Dirac's prediction of antimatter reappeared within the structure of quantum field theory as a natural result. Quantum field theory showed that the formation of particle and antiparticle pairs was inherent in the quantized nature of fields, illustrating how masterfully the universe was balanced in its symmetry between matter and antimatter. In the depths of the universe, a mysterious dance between matter and antimatter continued through the vibrations of these fields. This theory not only provided scientists with a new way of thinking, but it also paved the way for new experiments. Particle accelerators and colliders were designed to discover the particles predicted by quantum field theory. These experiments allowed us to discover new particles that form the fundamental building blocks of the universe, such as quarks, gluons, and carriers of the weak force. The discovery of these particles and the interactions among them revealed the vast complexity of the universe. Physicists could now understand how these fundamental particles interacted with each other and exchanged energy and information. The impact of quantum field theory was not limited to the microscopic world. It also spread to the broad horizon of cosmology. The principles of quantum field theory were used to understand the events that took place at the beginning of the universe, at the moment of the Big Bang. Questions such as how the cosmic microwave background radiation was formed and how black holes and dense stars behaved within quantum fields could now be examined in a new light. Through this theory, we began to understand not only the beginning of the universe, but also how galaxies, stars, and planets were connected, how space around black holes curved, and how matter moved on large scales. The profound understanding provided by quantum field theory allowed us to reconsider the four fundamental forces of nature: the electromagnetic force, the weak nuclear force, the strong nuclear force, and the gravitational force, with a new interpretation. It showed that these forces emerged from the interactions of particles and fields, and that the fabric of the universe was woven through these interactions. Quantum field theory also inspired advancements in technology. Modern technologies, such as semiconductors, transistors, and medical imaging devices, are based on the principles of quantum mechanics and quantum field theory. Even developments in medicine, such as radiation therapy and magnetic resonance imaging, are based on applications born from this theory. Thanks to quantum field theory and the second quantization, we now know that everything in the fabric of the universe is shaped by the vibrations of various fields. Particles come into existence and disappear through the excitations of these fields. How did quantum electrodynamics bring together electrons and light? In the 1940s, the world of physics was shaken by a new wave of discovery. Geniuses such as Richard Feynman, Julian Schwinger, and Shinichiro Tominaga embarked on a journey dedicated to unraveling the mysteries of one of nature's fundamental forces, the electromagnetic force. As we know, electromagnetism is the force that governs the interaction between light and electrons. However, understanding this interaction on the quantum level, within the uncertain and extraordinary order of the subatomic world, was impossible. The explanations of classical electromagnetism did not align with quantum mechanics. A new theory was needed to bridge this gap and help us understand the fundamental nature of the universe. At this point, quantum electrodynamics was born. Quantum electrodynamics explained one of nature's fundamental forces with incredible precision by establishing a link between electrons and light. This theory revealed the quantum-level interactions of electrons and photons, the particles of light. Quantum electrodynamics demonstrated how each interaction operates at the quantum level, describing the mysterious dance between light and matter. Thanks to this theory, we now know that light and matter are bound together, not just by ordinary interactions, but by deep symmetry and harmony. The Feynman diagrams developed by Richard Feynman provided a way to visualize these mysterious interactions. The diagrams transformed complex mathematical processes into maps that showed how electrons and photons are created and annihilated, and how energy is transferred. Each line, each arrow, revealed how matter and light interact on a microscopic level. Feynman diagrams exposed the functioning of the quantum world like a symphony. This tool was not only a mathematical innovation, it was also a journey of discovery that deepened our intuitions. Quantum electrodynamics made predictions that were in extraordinary agreement with observations. From measurements of electrons' magnetic moments to their interactions with photons, the predictions offered by quantum electrodynamics expanded our understanding of how nature operates. This remarkable agreement made quantum electrodynamics one of the most accurate theories in science. This success did not only explain the electromagnetic force, it opened the door to understanding other fundamental forces within the framework of quantum field theory. The success of quantum electrodynamics also inspired the understanding of the strong and weak nuclear forces, leading to the birth of the Standard Model, the fundamental framework of particle physics. How did John Bell propose to resolve the quantum reality debate? At the heart of the debate between Einstein and Bohr lay the question of whether quantum mechanics fully captured reality. Einstein argued that quantum mechanics was incomplete and that deeper, hidden variables must exist, while Bohr insisted that quantum mechanics accurately reflected the fundamental laws of nature. John Bell developed a mathematical framework, known as the Bell theorem, to address this fundamental issue. Bell formulated Bell inequalities, which demonstrated that if local hidden variables existed as Einstein suggested, certain measurable statistical outcomes should follow. These inequalities contradicted the predictions of quantum mechanics, making it possible to test experimentally which view was correct. The Bell theorem relied on a series of thought experiments that questioned the fundamental principles of quantum mechanics and the nature of reality. It focused particularly on the phenomenon of quantum entanglement. Bell showed that if local realism were true, that is, if physical influences could not travel faster than the speed of light, and if physical systems had definite properties before measurement, then the Bell inequalities should hold. However, quantum mechanics predicted that these inequalities would be violated. Starting in the 1970s, Bell inequalities were tested experimentally. In 1972, John Clauser and Stuart Friedman conducted one of the first significant experiments. In these experiments, entangled pairs of photons were used, and the results showed that Bell inequalities were indeed violated. Then, in 1982, Alain Aspect and his team in France conducted more precise and controlled experiments. Aspect's experiments more accurately confirmed the correlations predicted by quantum entanglement and clearly demonstrated the violation of Bell inequalities. In these experiments, the polarizations of entangled photons were measured, and the measurement settings were randomly and rapidly altered, eliminating any possibility of classical communication. The results of these experiments proved that Einstein's principle of local realism was not valid and confirmed the strange and counterintuitive phenomena predicted by quantum mechanics. The spooky interactions between particles, meaning the fact that a measurement on one particle has an instant effect on another, had to be accepted as a fundamental feature of physical reality. Is quantum mechanics the ultimate theory, or a gateway to new discoveries? Quantum mechanics is a revolution that overturned what we know about how nature operates on the smallest scales. It introduced us to the unimaginable strangeness of the subatomic world, which goes beyond the familiar laws of physics. In this realm, particles can exist in multiple states simultaneously, and reality remains indeterminate until observed. Quantum mechanics tells us that nature fundamentally operates with probabilities and uncertainties. Yet we face a question: is there a limit to our understanding of this theory, or does quantum mechanics fall short of explaining the deepest mysteries of the universe? Scientists like Roger Penrose are not satisfied with the probabilistic structure offered by quantum mechanics. Penrose believes that quantum mechanics should not just be a tool for prediction, but should evolve into a framework that reveals the fundamental laws of the universe. According to him, nature might operate not only through randomness and probabilities, but perhaps within a larger order, in a context we have not yet comprehended. Penrose's theories, suggesting a deep connection between consciousness and quantum processes, open up a new line of thought on how the universe functions. Does what we call quantum collapse happen merely due to observation, or is there another law within the fabric of the universe that causes this collapse? The answers to these questions may lead to a revolution in understanding consciousness and our own existence. This theory holds the belief that by combining gravity and quantum mechanics, known as quantum gravity, we may unlock the deepest secrets of nature. Quantum gravity might help us understand not only particles, but also the moment of the Big Bang and the singularities at the centers of black holes. Imagine if everything in the universe could only be explained by combining these two theories. In this case, quantum mechanics would serve as a gateway, a bridge to the deeper laws of the universe. As Penrose suggests, perhaps a journey that descends into the finest details of the universe's fabric depends on a grand discovery that unites gravity and quantum mechanics. The future of quantum mechanics includes not only theoretical questions, but also technologies that propel humanity forward. Quantum computers, remarkable tools inspired by this revolutionary theory, utilize the ability of subatomic particles to exist in multiple states at once, accelerating our calculations and taking information processing to another level. However, those who think like Penrose argue that, despite the extraordinary speed of quantum computers, they may not be able to provide the ultimate answers about the fundamental workings of the universe. According to him, even if quantum computers achieve significant success by pushing the limits of quantum mechanics, they may still fall short of unlocking the deepest mysteries of the universe. At this point, we are at a crossroads in science. Is quantum mechanics a final stop that will allow us to solve all the mysteries of the universe? Or is it merely an essential gateway in our journey of discovery? Penrose's critiques and proposed theories remind us that the universe may possess a broader, more complex, and perhaps far deeper structure than we imagine. Reaching the mysteries of the universe is a journey that has enchanted scientists of every era. Thinkers like Penrose see quantum mechanics as merely a temporary stage and strive to uncover nature's more comprehensive laws. Perhaps this search will lead us to a series of other unknown theories. Maybe one day, we will be able to explain the entire workings of the universe within a single framework. Science is a continually evolving journey that extends its own boundaries. The future of quantum mechanics may be shaped by these critiques, transforming into a great leap that brings us closer to the deepest mysteries of the universe. Seeking answers to these questions means opening doors to a greater understanding of the universe and ourselves. In this journey into the depths of the universe, quantum mechanics has led us to unexpected discoveries. Yet only time will tell whether this journey will end with the unraveling of all the universe's secrets, or with the arrival at the door of an even greater mystery.